let's do two isomorphism problems on this sort of go here. I want to do one that's kind of a shoe-in, that's real easy and not particularly challenging. And then I want to do one that is really quite challenging. So, in a small amount of space here, I want to do the easy one. In both of these examples, although it's kind of a spoiler, is they're going to fail to be isomorphic to one another. All right, let's do some names here. So here's G and H. Maybe I'll use letters for this and numbers for this. All right. Our claim here is that G and H are not isomorphic. Okay, so functionally speaking, we're saying an isomorphism cannot be found. All right, there are actual fairly low intelligence, high computation ways of doing this, right? Where you don't have to have a complex idea. You could brute force this. All right, you could. Let me write that down. You probably meaning a computer more than anything. You could brute force check all, and you would have to check all one-to-one mappings. Okay, and of course what would have to fail in every single check would be some sort of adjacency check, right? Clearly if you don't have the same number of vertices, there are no one-to-one mappings at all. The whole adjacency question you never even get to that. But at least hopefully I kept it at least interesting enough to notice that there are some one-to-one mappings here. Okay, because we have 4 vertices in G and 4 vertices in H. All right, another thing I kept sort of keeping this from being too extremely trivial, and that is there's 4 edges here, and there's also 4 edges in H. So G and H both have the same number of edges. If they fail to share the same number of edges, then there will never be a way to preserve the same number of adjacencies, right? So the vertex count and edge counts absolutely have to be equal, otherwise this is not even worth your time. So those are easy things to check. All right, so what else could we do? Well, you notice C and D are going to be somewhat difficult to use as sort of, what would you call them, sort of things to make this look impossible, because C and D are adjacent to one another, they're degree 2. Okay, so we'll define degree in a second, but they're each adjacent to 2 other things. But you could kind of work your way and say, okay, well if C and D are any pair here, it'd have to be either 1, 2, 2, 3, 3, 4, 4, 1, right? So there's 4 possibilities. Now C and D are mutually adjacent to another vertex B, and none of those pairs are mutually adjacent to another thing. That is a lot. You can always pick whatever you want to go with. I'm going to go with something much simpler. All right, so I'm going to go with A. A is adjacent to one vertex. We can even name it. It's B, but its name isn't super important. No vertices in H are adjacent. Boy, this is a bad looking adjacent. I think that'll work. No vertices in H are adjacent to only one vertex. So no isomorphism exists. Right. You could give a little more detail. You could say there's no way to create a one-to-one mapping that preserves adjacency because anything you map A to is going to have 2 adjacencies, and A doesn't have that. All right, so you can make it a little more verbose if necessary, but this seems to be plenty, and hopefully I want to give you things that you could write down when you're doing homework or exams sort of thing. Okay, so this is supposed to be an easy one, but you can already see, this can be a challenge. And you have to write stuff down, right? It's not a question of just writing down a few, like A looks to be a problem. Right? You have to actually say why. Alright, so let's do one that's more challenging. And it's one of my favorites because, well, I like the cube as a graph. Okay, this time I'm going to do A, B, C, D, E, F, G, H, like that. And then my graph, H here is going to be that stop sign looking graph, but it's going to be different this time. Right? Last time I did a version that was isomorphic to the cube, but I'm going to do something different this time. I feel like I'm really channeling Bob Ross in a lot of these videos here. That's not a bad thing. This time the connections are going to go crossways. Okay. And if you want to, you can make these crosses all meet in the middle, but who cares about that part? That's just the edge crossing stuff. Alright, and this one I'm just going to number and go around. Alright, so the easy things. Do they have the same number of vertices? Yes, so that's not an easy out. Do they have the same number of edges? That's probably not quite as easy to tell. There are 12 edges here, and if you go through and count, there's 4 in the middle, 8 are on the outside, so they have the same number of edges. Could I use this argument that a vertex is adjacent to more things in one and can't ever be matched to another? Actually, no, that doesn't quite work this time either. Every vertex in G is adjacent to 3 other things. And same thing with H. Every vertex in H is adjacent to 3 other things. Alright, so that is going to make things quite challenging at this point. So what do? Alright, well, there's a couple things. We're going to need to find features of one graph that the other graph does not have. Alright, and this is the thing about when you're showing 2 graphs that are isomorphic, there's not one way to do it. In fact, you need to build an entire toolbox that will continue to evolve over time, and work that way. So what I'm going to do is I'm going to show that G has a feature that H does not. Right, and this will show that they're not isomorphic, right? Isomorphic graphs should have the same features, at least as long as they're just graph specific instead of drawing specific, right? You can't say this one has a straight line, this one has a curly line, and so they're not isomorphic. You can't just say one's drawn different, right? That's not an explanation at all. But I am going to show you that G has a feature, and so let me go through and show you how this works. So I'm going to circle A, then everything adjacent to A. No, I'm going to try. Well, I think yellow will be. I'm going to use green because I think green and orange stand out really well. Everything that's adjacent to A, I'm going to give a different color. In this case, I'm going to use the green marker because it is different than the orange. Alright, now I go to every single one that's green, everything it's adjacent to, I'm going to circle with orange. So B is adjacent to that one, D is adjacent to that one, so E gets circled. Okay, and then I go to the orange and circle everything that it's adjacent to with the green marker. If you have 3 colors, more colors, you can do this. But so what I've shown here is that G is something called bipartite. I was able to successfully do this without any contradictions. In fact, I could rewrite this to show you what a bipartite graph looks like. So it looks like A, G, E, and C. I'm going to write them on one side. Okay. And then B, H, F, and D are on the other. Some 4 dots get started, and then I'll write those letters down. Doesn't really matter which ones I write where, as long as they're on this right-hand side. So B, H, F, and D. Alright, and then I'm just going to write down what A is adjacent to and connect them. So A is adjacent to B, it's adjacent to H, and then it's adjacent to D. So this is actually relatively easy. Alright, then I go to G. What is G adjacent to? It's adjacent to B. It's adjacent to F and H. So F and H. looking at E, E is adjacent to F, H, and D. So F, H, and D. All right, C is adjacent to D, F, and B. So D, F, and B. All right, so what makes a bipartite graph bipartite? So this is a new vocabulary word. All right, so I'm going to say it verbally. It's in the book too, so make sure you check the book as well. The word is got, the etymology is pretty descriptive here. The part means it's in two parts, and bi means two. So bi means two parts. Within each part, you notice A, G, E, and C. There are no adjacencies between them. Same thing between B, H, F, and D. There are no adjacencies here. So within the parts themselves, there are no adjacencies. The only adjacencies allowed are cross parts. So if you had a tripartite graph, you would do 3 groups, and the only adjacencies allowed would go across parts, just not within the parts themselves. Okay? So you could read this as a 2-part graph, but it's called bipartite. So this graph G is bipartite. I was able to demonstrate that. Okay, I can show you that H is not bipartite because this algorithm of searching by circling always works. Okay, we'll justify it again in this course by doing something called a breadth first search. That's actually all I'm doing here. Okay, so I'm going to do the same thing. Now, A and 1, I'm not claiming are the same. I'm just going to start at 1. Okay. Now, what is 1 adjacent to? Is adjacent to 2, 8, and 5. All right. And then I'll go to 2, 5, and 8 and circle everything orange that it's adjacent to. So A is adjacent. It's orange, 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 orange. And hopefully some alarm bells are going off, right? I go to the newly circled orange ones and I look at what's adjacent. 6 is adjacent to 7, so it should be green, but it's orange. 4 and 3 should be different colors, but they're not. Right? So this is a problem. So this is broken. So H is not bipartite. Okay. All right. There's some other reasons why these two graphs are not isomorphic. Actually, there's a ton of reasons. This is just my favorite one. And this is a skill that you really should learn because, first of all, you need to be able to tell if a graph is bipartite. So you need to be able to do this process. Right? It's either going to work, like it is in G, or it's going to fail in H. If it fails, it doesn't mean you need to try again. It turns out that success or failure are sort of just a binary thing. It's not coming down to you being bad at it or good at it, like you made the wrong choices. This process is going to work every time. And it has to do with the breadth first search sort of process. Okay, so G is bipartite, H is not bipartite, and if G and H were isomorphic, it would be one or the other. You can't just redraw a graph and have this failure occur. Right? You can't deform the graph and all of a sudden this fails to happen. All right, so this one's a harder example, right? Because you had to do something kind of unique and different. And this is not uncommon with isomorphism problems to have to do a fairly unique sort of trick to figure out why they're not the same. But there are some easy things. So for instance, one thing that we didn't get to take advantage of because they matched was sort of these vertex adjacencies, right? There's 3 adjacencies per vertex in both graphs. When those things start to fail to match up, or the ability to make a matching, that's a fairly easy way to get out of trouble, so to speak. So let's dignify that with a name. It's incredibly important. The number of adjacencies. And then in the next video, we'll do some stuff with these. That's super important. All right, so the number of adjacencies that a vertex has is referred to, sorry, 2 words collapsed together, referred to as its degree. All right, one caveat here. Self-adjacency is counted twice. Okay. All right, now why is that? Well, that's because the edge comes in with both ends. All right. So there's another way to define degree, which I'll give you that one as well. But you need something called, well, I don't have enough space to do it here, so I'll do that in the next one, and then we'll play with some stuff with degree. But this is probably the more natural definition of degree. The only place where it kind of is troublesome is when you have self-adjacency. So I'll give you the one that kind of captures the whole picture all at once as well, but they're equivalent definitions. All right, so I'll see you all on the next video.